Hello, everyone. We're continuing in Statistical Methods for Rates and Proportions, Chapter 6, Comparative Studies, Cross-Sectional, Naturalistic, or Multinomial Sampling, Section 6.4, Part 2, Mean and Variance of the Non-Central Hypergeometric Distribution. So we're on page 109 of the text, if you're following along. So we are going to create our same data set with maternal age and birth weights. And similarly to how we've done in previous sections, we're going to set up the table of the joint frequencies and the table of the joint proportions. So we're going to also identify P11 all the way through P22 by picking off using the square brackets, row and columns of each of the proportions tables. We're going to use the apply function to get all the marginals. And we're going to get all of the counts as well. So n dot dot is the overall sample size, n11 is the frequency based on t, and then n1 dots down through n dot twos, those are the marginal frequencies. So we've assigned everything, and similar to before, we're going to also calculate the odds ratio by getting the odds of A divided by the odds of not A. And here, if we look at T one more time, we can see that A adds up, the marginal for A is 50, whereas the marginal for B is 25. So when we think about X, it can only range this value right here, the first cell, can only range to the smallest values of the rows versus the columns, because if we set the marginal frequencies to be fixed, then this value can only be as big as the smallest of the marginals. So here we're setting X to be from 0 to 25, right? And we're going by 1. All right, so in a very special case where omega equals 1, then the reference cell, right, can only be as small as 0 or as big as 25. And we have a formula that can calculate the mean and variance, okay? This is given in equation 6.40 in the text. And we can calculate the mean and variance as given in those formulas. And then I'm going to use the paste function here, which will allow me to insert text mixed with values of numbers, mixed with more text, and mixed with the values. So here I tell R to say, when omega equals 1, the expected value of X is 6.25 and the variance is 4.12. So what that means is that if we're looking at this table where the marginals are 50 for the rows and 25 for the columns, then this first cell, I would expect the value to be 6.25. And the variance here is 4.12. So I observe a value of 10, but I expected to see 6.25 if A and B were unrelated. All right, so that is a little simpler when omega equals 1, but if we want to, we can also calculate the exact mean when omega is not equal to 1, right? And so now I'm looking at equation 6.43 in the text for the expected value. And you can see that there is a summation in the numerator and a summation in the denominator. So what I'm going to do is I first notice that the endpoints of the summation are the same in the numerator and the denominator. So I'm going to just set my endpoints here. I'm going to make sure that I've ran the hypothesis that omega equals 5. All right, so for the numerator, this is I times n dot 1, choose I, times n dot 2, choose n1 dot minus I, times omega to the I, right? And if you look at that, that is the definition for expected value, right? You're taking your X times your PMF. And the denominator almost looks equivalent, but if you notice, there's no multiplication of I for the denominator. So what I'm going to do is I'm going to initiate my numerator and denominator just to be an empty list before I run my for loop. And then I'm going to use a for loop to calculate each of those values in the numerator and denominator. Okay, and if I wanted to, I could just say, what are all the values in my numerator? And if I looked at that, I'd get all the different values. And similarly, I could look at that for the denominator. Okay, but really at the end of the day, this equation 6.43, it says to sum up all those pieces, individual pieces that we calculated in the numerator, and divide that by the sum of all those individual pieces we calculated in the denominator. So if we want to get E11, we're going to use the unlist function. We're going to say sum of the unlist of the numerator, and we're going to do that same thing for the denominator. So we'd get the value of the E11. So if we hypothesize that the odds ratio is equal to 5, well, then we would say that we would think that that very first cell, we expect to see a value of 14. Okay, so essentially what we're doing is we're trying to say, based on our hypothesis, what would we expect the table to look like? And then we're going to compare our observed table to that expected table to see if what we thought was really true. All right, continuing on in equation 6.43, we can also get the expected value of each of the other cells, right? So we can get E12, E21, and E22. So using those formulas, E12 is just N1 dot minus E11, right? And then E21 is N dot 1 minus E11. And then if we think about E22, then we can also get that by doing E11 minus the sum of the marginals minus the overall sample size. So from there, we can look at all of those values at the same time. We can get each of those E11s, so that's the expected value of the 1 cell, the expected value of the first row, second column, the expected value of the second column, first row, expected value of the second row, second column. So we can compare those values to T if we wanted to, right? So we expected 14.14, we saw a value of 10. We expected a value of 35.86, we saw a value of 40. We expected a value of 10.86, we saw a value of 15. We expected a value of 139.14, and we observed a value of 135. All right. So to get the exact variance, we're going to apply a similar technique using equation 6.44. And we are going to essentially just take what we see in the equation and use R to make all the calculations at once versus having to do it all by hand, right? So we have our numerator, we have our denominator, and we look at this equation. This is the regular way of calculating expected value, right? We do our I minus the expected value, quantity squared, and then we multiply that by the non-central hypergeometric distribution. All right, so I can use this function that says if you tell me what E is, then go ahead and calculate the variance. Okay, so this is essentially 6.44. And here I can get the variance by saying, what's the variance of the 1, 1 cell? Well, I'm going to feed the function E11. And then I can feed the function E12 and so on, right? So here I can get the variance of each of the cells by using that formula. And so I have the corresponding variances for all the expected values. You can check this next to the book on page 110 to see how these all work out. But it's really nice that you don't have to do all of this by hand, that you can use the formula, create a function in R. From that function in R, it can automatically calculate the variance of all those values. Okay, I hope you learned something in this video, and I will see you guys next time.